Broadcast is now starting. All attendees are in listen-only mode.
Welcome to our AMS webinar. Actually, this is our first AMS webinar in the 2022. We've just finished releasing all our 2022 products, and we're going to start a brand new webinar series this year. We're going back to basics, starting with 2.5 axis and 3 axis machining. The reasons are we've done this before in the past, but we want to cycle back because the product has changed quite a bit. We've added a lot of new functionality, and so we wanted to go back to basics and start from the beginning and then work our way up to more complex topics through the year. So welcome again. My name is Joe Anand. I'm the product manager here at MecSoft. And today I'll be joined by Don LaCourse, who's our senior application engineer, who's actually going to be doing the demo and the webinar, running it. I will be in the background waiting for your questions, listening for your questions. And then please feel free to type in your questions. Don, the next slide, please. In the chat window, to type in your questions in the chat window. Get where the arrow is pointing, you can see that's where you type in, and I'll be in the background watching for it, and I will answer it, and if necessary, we can stop Don in the demonstration to get some of the questions answered if it's of general interest. Please reserve specific questions either later in the 10 minutes or where we reserve for the question and answer session, or you can send us email for any specific questions that you might have. And we are recording this webinar, and the recording will be made available in a day or two once we get the webinar done and the recording cleaned up, and we'll send it out to all the registrants. And let's talk about the agenda for this webinar. We're going to start out from the basics. As I mentioned, 2.5 and 3 axis explained what it is, and understanding machines and setups in our product. How do you set up machines, and also how do you create setups for machining? And then also how toolpaths are actually calculated by the system. An internal understanding of how this is done might be useful when you're programming or when you're creating toolpaths. We'll talk about cutting tools, control geometry, how we can use control geometry for controlling where you want to machine and how you want to machine. Cut levels for different cut methods. This is an important topic that a lot of people initially have difficulty. And then understanding stock models and also stock allowance. And then talking about finally about post-processing basics. We'll just touch on it very briefly because this is an introductory webinar. And then finally, tips and best practices for new users. So without any further delay, we'll turn it over to Don. So Don, go ahead.
Hello, everyone. Thanks for joining us today for our AMS webinar series. And it looks like we have a number of new users attending. So thank you for being here with us. So we're going to start out by just going over the typical workflow that you would take when you start any CAM job with our MecSoft CAM products. We're going to start up in the top left corner, and obviously you're going to load your part and you're going to define your stock geometry, not mentioned, but also you define your setup, everything that you need to start programming the part. So if we take the arrow to the right, the very top, we see 3 balloons in the middle. Create roughing operations, create pre-finishing operations, and create finishing operations. Now, depending on your part, what you need to do, you may not need a pre-finishing, you may just need a finishing. So, but this is an idea of the process that you're going to take. Now, if you move to the right, the far right, you see simulate material removal. And you see that arrow goes to the left and the right. So anytime you create a new operation, you want to simulate it so you get an understanding of where that tool is going to go, how it's going to cut. And you want to do that every time, like I mentioned, every time you make an edit, but also every time you add another operation, because for instance, a second operation will be based on the cut material simulation of the first. So you need to do a complete simulation of all of your operations to get a clear understanding. And there's some users who they get comfortable using the product and they decide that they don't need to do a simulation. Well, I'm going to tell you, you need to do one every single time. Even if you understand what's going to happen and it's not really complicated, it will highlight areas that you may not have thought about, and it'll protect you from possibly damaging a tool or some stock. Now, we'll talk very briefly about the machine and the setup. We've got two graphics here. The one on the left shows the default setup when you run the product. So when you run the product, you'll see that you have one setup defined in your machining job called setup one. That setup, the orientation, meaning the X, Y, and Z axes, by default are aligned with your world origin in the CAD system. So by default, the X is to the right, the Y is looking into the machine, and the Z obviously is pointing up to the machine spindle. So for the express, standard, expert configurations, this is the setup you're going to see, and you can't change that in those configurations. You have one setup, and if you need to move your part around, then obviously you can't move the setup, so you have to move your part if you need to orient it properly or a different way than you want to. So on the right, in addition to defining a setup that matches the coordinate system of your machine, you can also add what we call work zero. So by default, when you open up a new drawing or model to machine, like I said, the setup one is aligned with the world origin. Also, that becomes the zero origin location to calculate your tool paths. You can move that origin, okay? Even in the standard, in the early configuration, you can move that origin by creating a work zero and put that work zero underneath your setup one, and you can define where that work zero is, whether it's at the top of your stock, bottom of your stock, however you want to locate that work zero, and then that work zero will then become the coordinate origin for all tool paths. Okay, let's talk a little bit about geometry. In our CAM products, you can program tool paths with just lines and curves. Like you may have a wireframe drawing. Typically, wireframe drawings are not used much anymore. But if you had just a 2D drawing, top view of a part that you needed to machine, you could use that in conjunction with 2.5 axis toolpath methods to machine your part. If you're going to work in 3 axis, you do need to have a part model. You need to at least have a surface. Okay, it doesn't have to be a solid. You can machine just a single surface in 3 axis. Typically, though, you'll have a poly surface or a group of surfaces, or a closed poly surface, which is actually a solid model. So you can use solid models, open poly surfaces, etc., for 3 axis. Now, the bottom left part, you can use 2.5 axis methods on a 3D solid as well. So on the far right, you see a mesh object. These are produced by point clouds, which in turn are produced typically by a scanning device for scanning a part that you want to reverse engineer back into the CAD system. And you can also machine these faceted mesh data with 3 axis methods. Now, let's talk a little bit about the difference between 2.5 axis and 3 axis. Basically, it's defined in how the tool moves. If you look on the left side, you'll see that the tool, we have a red arrow X and a Y arrow Y, I mean a green arrow Y. The tool can move in these two axes simultaneously, but it's fixed in its Z axis. So you define the depth of the tool to cut, and it will stay fixed at that depth and move in X and Y. So, and the movement in X and Y will be contained by the control geometry that you select. Now in 3 axis, you see that we have a third Z axis in blue. So in 3 axis, the tool can move in the X and the Y and the Z simultaneously. It may not be moving in the Z at all times, and it may not be moving in either the X or the Y at all times, but you know, it will and can move in all 3 directions as needed at the same time. So that's just real basic understanding of the difference, how the tool moves in both 2 axis and 3 axis. And if you look on the right also, you see a boundary curve at the base of that part. You can contain your 3 axis operations to the control geometry that you select. So basically the underlying part in 3 axis is controlling the tool, because it won't gouge the part. It'll use that part as a guide to cut over it. Now let's start out by talking some basics about 2.5 axis machining. What you see here on the screen is the XY view of a part, 4 different parts, and you see the red dots are the tool diameter looking down on the XY plane. So what we're trying to convey here is we want you to understand how that tool is going to behave when it reaches, or when it is controlled by the control geometry that you select. So on the far left, in a facing operation, the tool center point of the tool will stop on the control geometry. So it's going to cut right up to the edge of the control geometry, and your tool is going to stop on the control geometry itself. If you look at the second from the left, you'll see a pocketing operation, and the tool diameter of the tool will stop when it makes contact with your control geometry. And you also, in both in the facing and the pocketing, you have a offset distance that you specify also, which will be used to offset the tool and clear either a face, top face, or a pocket. Now, if you move to the right for profiling, the contact points is identical for pocketing, except that you're not clearing out all of the material inside. You're probably assuming that you've already cleared it out to some extent, or maybe used a pocketing operation and left some stock on the sidewalls. So you're going to use a profiling operation to finish the sidewalls, and maybe even the depth of the pocket. Now, all the way to the right, which is a very versatile operation, you really should get to know your engraving operation. In engraving, the center and the tip of the tool will follow your control geometry wherever it goes. If that control geometry is tapered on, it's a 3D curve, you can use the 2.5 axis engraving to follow that curve. It'll follow it wherever it goes. So that's a good operation if you want to engrave some lettering on a part, or if you want to tell exactly where you want that that tool to move, you can just draw the control geometry curves, and you can use that as input to your engraving operation. Now, this is the basic the four basic operate. There are more advanced operations in profile. I mean, in 2.5 axis, but we're just touching the basic operations.
I'll add a quick note here, Don.
Yeah.
One of the things that the way you can think about facing and pocketing is you can think of facing as you're machining cores. And then if you're from the mold making world, you can think of facing as the outer boundary actually represents the outer air to be machined, so the stock to be machined, so you can approach the part from outside. So it's really a core type of machining operation. While pocketing, you're machining a cavity where you cannot enter from the outside. It's enclosed on all sides, so you'll have to enter inside of the perimeter of the control geometry. So if you're oriented that way, that might make it easier to think about facing and pocketing in that fashion. Thanks, Don.
Okay. Now here is just an isometric view of each of those examples. As Joe mentioned, if you start on the facing on the far left, you'll see that the control geometry extends out to the perimeter of the part to clear the entire face. And for facing, obviously, you can use flat end mills, and facing mills, etc. Again, the pocketing, obviously, we talked about that. The flat mill is extending till it touches the control geometry at the perimeter of the pocket. And the same with the profiling. And then the engraving operation on the right, I showed a round slot. You don't have to have any geometry other than a curve for that tool to follow. I just showed a slot just to give it a representation of cutting around that control geometry. In this case, simplified case, just creating a rounded slot. Now let's talk a little bit about, you're going to want to understand how the tool is going to cut, how it's going to start cutting, and what side of your control geometry is going to be cut. Because you have different options in the cut parameters tabs of the 2.5 axis operation types to tell right side, left side, inside, outside, etc. Just so you understand what right and left means, if you look at the top left illustration, you'll see that we have just one line, one curve, starting at the bottom and continuing to the top. If you see the little squares there on those geometries, those are the start points. That is, anytime you draw a line or a curve, by definition, it already has a start point. If you draw a line from point A to point B, point A will be the start point as defined by the CAD system. So if you machine on that line, the start point is where the tool is going to start cutting. And the right hand or left hand, obviously, if you're standing at the start point and looking down the curve, right side is your right side, obviously, and left is your left side. And that's also the case in closed curves. If you have a circle has a start point and it has a direction. So if you're going to want to machine the outside, that would be the right side of the circle in this case. If you go on machine on the inside, that could be the left side or the inside. And
quick note on this slide actually applies mostly to the profiling machining operation, because the curve direction on the right side and the left side all come into play only in profiling. As we mentioned, in facing and pocketing, the curve determines, the closed curve determines the side, because in pocket it's always on the inside, and on the facing it's always on the perimeter. Right. So we're really talking about the profiling machining operation here. It's important to know.
Thanks, Joe. Also, just on an open NURBS curve is the same. You have a start point and you have a right and a left. If you look down below that, you see using multiple curves. On the left, you see we have 1, 2, 3, 4, 5, 6, 7, 8 curves that are closed, but they're not merged into one single curve. So you see start points at each of the curves. We highly recommend that if you're going to machine more than one curve, is that you merge that into a single curve. And if you're on the right, you'll see that it has a merged curve, has one start point, and it's closed continuously. So that that is the method you really want to strive for if you're going to do any curve machining. Obviously it's more than one curve. So always remember to join your curves or merge them together. And then on the right, we just see the different indicators of the start points and directions of curves. So basically, understand here in profiling, the tool is going to start at the start of the curve. It's going to do a cut on the side of the curve that you specify, right side, left side for an open curve, inside, outside for a closed curve. Now let's talk about a basic understanding of cut levels in 2-axis. You may have seen, if you look at this dialog on the right, you probably have seen this dialog, and it may be a little intimidating at first. But once you understand what it's doing, you'll see that you have absolute control of the depths of your cuts. So at the top of that dialog, you have location of cut geometry. Now, just ask yourself, the control geometry that I selected, where is it in relation to the depth of the cut? Okay, is my control geometry at the top of the cut, like on the top right image? Is the control geometry at the bottom of the cut, like in this image here? Or if your control geometry is not on the top or the bottom, or if you want to specify a different top position to start cutting, you can use the pick top. Now, you can use the pick top, and just one basic example, if you want to face off your spool board and you want to cut below your typical bottom of your part as it sits on the spool board, you can use the pick top, and you can define the top where it's going to cut, and you can give it a depth, and that depth may extend down past the bottom of your part, and that's where the cut levels will end. One thing to note, if you use the at bottom, the tool will not go past your control geometry. That's where it's going to stop. So it's going to start, it's going to work its way back for the total cut depth. If you end at the bottom, it's going to calculate upward your total cut depth and start cutting there, and then cut your rough depth per cut at each level. Now, a little bit more about this dialog on the right. If you look at that illustration, the dialog icon, it tells you how this is working. So you got the location of your cut geometry. In this example, it's at bottom, okay? And for the total cut depth, it's 3/4 of an inch. So if you look at the total cut depth on the left side of this illustration, the total cut depth starts or ends at the bottom of the control geometry, and it starts, the total cut depth works its way up and starts there and works its way down. Now, the rough depth per cut and the finish depth, you can break this total cut depth into two parts: a rough depth area and a finish depth area. Now in the picture here, you see the light blue or cyan lines. That is the finish depth. The dark blue lines is the rough depth. So you can tell it with these two sliders down below, what is my cut level for the rough depth area and what is my cut levels for the finish depth area. So that's just some basic, and you'll see these options on virtually every 2.5-axis toolpath dialog. Now let's talk about how basic tools interact with your control geometry. And this is very critical that you understand how these three tool types are going to act. So typically for 2-axis, you'll use a flat end mill, cutting pockets or cutting profiles, or facing. You can use a flat end mill for facing. In the image here, you'll see that the diameter of the tool stops at the side wall of the control geometry where the little square is, okay? The red dot is the program point for the tool path, and you'll see that the blue lines extend out, stop at the center of the tool, and each one of these are cut levels down to the bottom That's a typical basic 2.5 axis pocket. Now the middle image, you can use tapered tools in 2.5 axis. If you have a chamfer on an edge that you want to cut, you can use a tapered tool. What's going to happen here is that the taper of the tool is actually the flute length, okay? And the taper is going to come over and stop at the perimeter of your control geometry. So the deeper the taper tool goes down, the earlier it's going to stop. So you can see the red dot, and then it slants to the left all the way down. So at the bottom of the pocket, the center of the tool would be here. So you can use that obviously to cut chamfers. Also, you can use it to cut drafted walls. If you have a constant draft on a wall and you have a taper tool to match that angle, you can use that to machine that draft. Now let's look at the one on the right. It's important that you understand how a ball mill is going to act in 2 axis. The tip of the tool will stop on the perimeter of your control geometry. As you can see, we stopped the tool at the very first cut level, and you'll see that the arc radius of the tool touches the control geometry. This typically is not what you want to do, especially if you're machining molds. Obviously, if this area right here was a parting line, you don't want that cutter to ride that parting line, because it's going to cut that edge at 1, 2, 3, 4, 5, 6, 7 levels. That tool is going to recut that edge 7 times, and you're going to have tolerance builds up. You're going to have just a sloppy edge right there. So typically you won't use a round ball mill for a pocket. Now for profiling, if you're just going to cut at the bottom of the pocket, if you want to leave a profile in your part, you can use a ball mill and just run it at the bottom of the pocket around. And actually our part that we're going to demo actually uses a corner radius mill that incorporates the radius into the part, and I'll show you that. So these are the basic understandings. Go ahead, Joe.
Yeah, quick note on the ball and mill. Actually, good 2 notes. What we're looking at here in the profile that Don has just shown, we call this the waterfall effect. So you can think of it as the tool is contacting that edge and it's waterfalling over that edge. And the middle picture, we call that the chamfer effect. Again, the same thing. It's contacting the side of the tool, and you're seeing that chamfer. One important note: a lot of new users get caught up on this. I just wanted to mention, if you're using a ball and mill and you select the curve as your machining geometry, as Don is showing here, but did not specify any cut depth, then you're going to get 1 cut level, which will be right on the same level as that curve if you have selected a big top. So, but if you're using a ball and mill, this red dot is actually going to be right on that curve. So you're not going to get any offset at all. And this kind of throws a lot of new users. They're saying, why am I not getting an offset? The reason you're not getting that offset is because the contact point of a ball and mill on the control geometry is right on it at that particular cut level. So that's something important to watch out for. So, thanks, Don.
Thanks, Joe. And again, if anyone has questions, go ahead and add them. I see we got a few questions. That's great. We'll get to them here shortly. Okay, let's move right along. Let's talk about cut our stock allowances in 2.5 axis. In 2.5 axis, the stock is measured on the side of the tool, the side walls of the part. So we got in this dialog on the left, we got 0.1 for stock. That 0.1 is measured on the side walls of the tool. And if you look in the illustration on the top right, you'll see the stock remaining is extending in the X and the Y direction of the part. So that's basically an understanding. Remember that stock is not automatically applied to the bottom of the tool on the bottom of a pocket. You control that with your cut levels. So the slide previous. Now let's talk about 3 axis. Similar to how we talked about 2.5 axis, we have 3 examples here looking down in the XY plane. On the left, all 3 of these operations are parallel finishing operations. Okay, so we have control geometry, which serves as containment to contain the tool path. And in finishing operations in 3-axis, again, the tip of the tool will go to and stop on the control geometry you select. So in this example, the tool is going right to the edge of the geometry, it's stepping over, coming back, stepping over, etc. In the middle picture, this is actually looking down on a sphere. So in this illustration, we selected the perimeter of the sphere at the split point of the sphere. And similar to the left image, the tool goes right to the edge of the control geometry, which is the right of the edge at the sphere, and it comes back and forth, steps over, etc. Now, the one on the right, if you notice, so you probably already, I'm going to show you this in more detail in the next slide, you're probably going to wonder, well, this tool is not going to reach all the way down, to the perimeter or parting plane of that sphere. So there's times when you want to offset this control geometry outward to give the tool more room to get down around the side. So let's look at this next slide and you'll see it in more detail. The one on the left, we're doing a parallel finishing on a flat area, and the tool stops at the perimeter. And in the center, new users don't understand yet that in parallel finishing, the center axis of the tool will stop when it aligns itself vertically with the control geometry. So if you just use the perimeter of your sphere, or if you just select the sphere itself, it's not going to go all the way down to the parting plane. It's going to stop when the tool center line aligns with the control geometry. If you want it to go all the way down, this is when you want to actually draw an offset curve. And you're going to do this a lot in 3-axis, and you're going to want to adjust this offset depending on what you want that tool to do in that area right there. It may be a little larger than the tool radius, but typically it won't be any smaller than the tool radius. And then also the green surface. What will happen if that surface is not there and you offset the control geometry, the tool will come down, and when it touches that control geometry, it'll immediately retract to the clearance plane. It will not go any deeper than your control geometry. It won't gouge, it won't risk gouging any material, so it'll retract. So that's why you have a plane there as a reference surface to eliminate all those retracts. It has a place for the tool to stop, do its transfer motion, and then start up again. So this is a concept you really need to understand starting out in 3-axis machining. Again, in 3-axis, you also have cut levels, both in roughing and in finishing. We have an example here on the left of a typical horizontal roughing cut level. And if you look at the dialog here in the middle for the cut levels tab, you can determine how you want the tool to step down. You have different options for how much of a step down you want to use. You got minimize stair steps. This is a more advanced function. We'll talk about that at a later time. You can tell it, do I want to cut all the way down in a pocket before I go to the next pocket, or do I want to clear it by levels? And then cut levels, you also can set some containments. Don't go any deeper than a certain dimension. Don't go any higher than a certain dimension. Or if you want to make sure the tool clears a flat area and puts a tool path right on a flat surface, you can check this box here. On the right, we have what's called a Z containment tab in 3-axis. This allows you to control the cut levels in 3-axis. You can give it a range. You can tell it don't cut any higher than this location, any deeper or any further down than this location, and you can tell it to cut in multiple levels. So in 3-axis multiple levels, it'll cut the level. When it gets to the actual part, it'll start cutting the contour of the part. Just one second. Now here, and this is talking about how stock is calculated in 3-axis. So if you look in each of the horizontal or wrapping or parallel finishing, either of the 3-axis operation dialogue, you have a value for stock. Stock is calculated. If you look at this closely, you see it's got a stair step for the cut levels, and it'll leave the amount of stock from any point on the perimeter bottom edge of the tool away from the part surface. And if you use clear flats, you'll see that it cuts right down on the flat areas. That'll clear that stock from all the flat areas. And then in finishing, the same goes. If you leave a stock amount of 0.1, it's obviously going to leave 0.1 of stock all around the contoured areas. Now, let's talk about just basic post-processing here. On the left, you see the post-processor dialog. We have added over 600 posts to our 2022 product. So we got tons of post-processors. More than likely, one of those will fit the tool controller on your CNC machine. You can start out with one of those. If you run into any issues or any alarms or whatnot, just let us know and we can help you make some adjustments to that post specific to your machine. And then in the center posting, obviously you can post an operation, you can post the entire setup, or you can use the control key and select multiple operations, right click and post those. And obviously example of some posted output. Okay, now we're going to go through this real quick. These parts that we're talking about here, we do have a tutorial already worked up for you. If you go to the online help, I'll show you if I have time exactly where to go, but go to the online help, select the resource guide, go down to the mill module, and you'll see these two tutorial PDF documents using the same parts. And again, we have 2 documents for tips and best practices in 2.5 and 3-axis. These are must read when you have time. Look at these. It'll give you a lot of good tips and a lot of good practices to use. Okay, let's get right into the demo. We got about 20 minutes left. So let's start our demonstration. So this part, this is our 2.5 axis prismatic part. Here, we're going to work our way from left to right from the program tab. For the machine, in 2.5 and 3-axis, you really only have one option. Keep it at 3-axis. If you only have Express, Standard, or Expert, you will only have one option called 3-axis. So that's what it's going to be for both 2.5 and 3-axis. And obviously, there's other options here that we'll get into those in a more advanced setting. So it's going to be set to 3-axis by default. Pick OK. So what I was mentioning here in the setup, you have by default, you have a setup 1 predefined anytime you open a part file or open a new file. And you'll see that if we turn this triad off, you got 2 toggles down here, one for the world coordinate system. So there's your world origin. And then by default, the setup is located at that location. And the X and the Y in the Z axes will align with your machine axes. Typically, if you're standing in front of the machine, X is to the right, Y is looking at the machine, and Z is up. So let's go ahead and do some 2.5 axis operations. We'll go ahead and start with a face top. So in face top, it just automatically determines where the top of the part is, where the top of the stock is, and it'll face that off for you. Let's go ahead and use a face mill. And for these examples, we're not going to get into feeds and speed values. We're just using the default parameters. In the clearance plane, you have options to determine how you want the clearance plane to be calculated. Typically, in most cases, you just select automatic. And then for transfer methods, you'll set it to clearance plane. So for the cut parameters in facing, you have a stock allowance and a tolerance. In facing, typically, you know, the tolerance doesn't really come into play a whole lot because the tool is going to extend past your part in the XY axis anyway. Stock, again, is measured in the X and the Y. It's not going to come to play in this part either, not in facing. So let's go ahead and we'll set multiple step overs, and we'll let the program compute the cut angle. And for the cut levels and face top, we're going to tell it that the top of the stock is going to be the top of the cut, and the top of the part is going to be the bottom of the cut. And for entry and exit, you got various options for entry and exit for the toolpath. And again, you got advanced cut parameters. Let's go ahead and generate this. So you'll see that we got a facing operation located on the top. If you don't want to do those retracts, you can change your cut direction to climb, conventional, or mixed. It retracts and starts a new cut if you're trying to maintain a climb or conventional. So we'll set it to mixed, and you'll see that there's no offsets. And let's go ahead and simulate this real quick. Slow this down some. And that's our facing operation.
Actually, that's our face top operation, which
Yep.
is really used for facing to the top of your stock. So if you have not a very smooth stock model or a stock, workpiece, and you wanted to face it so it's to the right level, this is what you use. And then we also do have a facing operation, which you can use for core type of parts.
Okay, let's go ahead and do these pocket areas. We got 2 blind pockets and 2 through pockets. Let's go ahead and do a 2.5 axis pocketing operation. And you'll see on the dialog, you have different buttons down here, different ways of selecting your control geometry. If you have flat areas, the fastest way is just use the select flat area regions button, pick the bottoms of the pockets, and it will calculate each perimeter curve for the pocket. So for the tools, we're going to use a flat end mill this time, and use the default feeds and speeds, same clearance, plane definition. For pocketing, obviously you have a tolerance. Each operation will have a tolerance value, and they come into play more often than not in different operations. And we have a stock value left. We're going to go ahead and leave no stock, so we're going to cut right up to the side wall of the pocket. And also you can enable cutter compensation. We're not going to get into that in this basics class, but we will probably talk about this in the future. We're going to use an offset cut pattern, a mixed cut direction. We're going to start on the inside of the pocket, and we're going to step over 25% of the tool. And let's go ahead and look at the cut levels. Where is your geometry that you selected? It's at the bottom. So that's how that works. Let's think about your geometry. Where is your geometry in relation to your cut depth? So the total cut depth, you can go ahead, if you know what it is, you can enter it, or you can use the pick button and select 2 points, doesn't matter which two, top and the bottom, and it'll calculate what that depth is. So it's 0.551 inches. So right now, if you leave it like this, it'll only cut one level at the bottom of the pocket. You can use this slider to add multiple cut levels. So let's go ahead, and for the pocketing entry and exit, you have different entry methods. We're going to leave it at a path entry and a linear retract. Again, since we have radii in this pocket, we're going to use arc fitting, and by a standard arc fitting tolerance will be 2 times your cut tolerance. So this tolerance is 1,000th, so we're going to use 2,000ths for arc fitting. So let's go ahead and generate that. So you see, sorry about that. So you see your tool path. Let's go ahead and show that. And let's go ahead and go to multiple cut levels. Just 1 second. Sorry about that. So you see this icon here allows you to see the cut levels inside of the part. So you'll see that we have multiple cut levels going down to the bottom of the pocket. So let's go ahead and run a simulation on this. We'll turn the toolpath off. And so you can see the entries and the exit at each cut level. Just speed that up a little bit. Okay, so there's our two pockets, and we got two other pockets. So what we're going to do is we're going to right click and clone this pocket, and then we're going to edit this pocket. We're going to remove that geometry, and we're going to add this geometry here, and we're just going to select the top edge of these two circles. And for the tool, we'll use the same tool. Everything's going to be the same. Tolerance be the same. We're not going to have any stock. 25% step over. The cut levels. This is a deeper cut level because it's going through. Let's go ahead and double check what the depth is. So it's going to be approximately 748, and we'll just make a couple of cut levels. Again, we'll use a path entry for the pocket, and we're going to use cut arc fitting. So you see,
there was a question on what is arc fitting. I just wanted to quickly explain what that is, and
let me make a correction here real quick. Location of cut geometry, I picked that bottom from the last operation, but it's not. The top of the cut is the control geometry, so I need to change that to add top and generate. Okay, arc fitting. What's going to happen here is when, if you don't have arc fitting enabled, it will create linear segments to cut that part. So the perimeter of this circle will be small facets going around because it's using.
Unless I want to qualify that statement, unless that perimeter actually is an arc. If that was a true arc, then it's not going to be linear cuts. It's going to be the toolpath itself is going to consist of arcs. But if we had linear segments as part of the perimeter, then the toolpath will also be linear segments. In those cases, you would want to use arc fitting to actually fit arcs after the toolpath is computed.
Mm-hmm. Okay, so let's go ahead and move on to our perimeter of the pocket of the part. We're going to use a profiling operation, and we'll just go ahead and we have a curve right here. We're going to select that, and we're going to use the same tool, cut parameters. It's going to be, that's fine. You use the midpoint of the longest side for the start point. We're going to use a 3D model to detect which side to cut. And for the cut levels, again, we're going to select the top and the bottom. We'll make an adjustment here, and entry and exit. We'll go ahead and use lines and arcs, and we're going to put those entry exits at each cut level, and we're going to use an offset overlap to clean up the area where you started cutting. And again, we're going to use arc fitting. We'll go ahead and generate that. So you'll see that the tool, when it goes around, a little bit too fast. When it goes around, it overlaps the start area and cleans up this part. So let's go ahead and just simulate those all the way through. So there's your part completed. Okay, let's jump over to the 3-axis part. Hopefully we'll have time to get through this real quick. If not, we may stay just maybe 5 minutes later. Okay, so here you'll see that part from the presentation. We have a half of a hair dryer, and what's interesting about this is it lies on a flat plane. This particular part is going to be used for a thermoform core, which it's going to heated plastic is going to be vacuumed down on top of this. So what you want in this particular part that's not shown in the part model is a fillet around this edge, and you can do that using the 3-axis operations and a corner radius mill. I'll show you how to do that. Now, why do we have these curves? as we mentioned in the presentation, we want the tool to come all the way down to the bottom. So we need to select a curve that's offset out from the perimeter of the part. So this red curve is 1/8 of an inch. That's exactly the fillet that we want at the bottom. But because this part has contoured areas, that's not going to be true for all of the areas going around it. So we have a little bit larger offset, which is about 0.13 or 1.5, a little bit larger than 1/8 of an inch. And then we have another one at 1/4 of an inch. So let's go ahead and see if we can get through this. So we're going to do a horizontal roughing, and we're not going to select anything. So when you don't select anything, it calculates the difference between the stock model and the part model. So it's going to calculate where it's going to need to cut. So for the tool, we'll go ahead and use a corner radius mill. Now I'll show you that tool in just a second and explain why I'm going to use that. And we'll go ahead and skip over to the cut perimeter tab. We got in 3-axis, you have an in tolerance and out tolerance. So that just determines which side, it allows it to deviate, on that stock around that contoured part by certain dimensions. And we're going to leave 25 thousandths of stock. We're going to use an offset cut pattern. We're going to start on the outside. We're going to have a step over of 25% of the tool. And let's go ahead and for the core facing, we'll leave that at island offsets. And for the cut levels, we're going to leave it at 50% of the tool diameter for each cut level. And we're going to do a clear flat. So we're going to put a tool path right on the bottom of this surface. For the engage and retract, we'll leave it at a helix. And advanced cut parameters, we have arc fitting. And let's go ahead and generate that real quick. Turn that tool path on. And let's look at this. And you'll see the multiple cut levels working its way down, and it added another level right on the flat area. So let's leave it now. I want to show you something I want to show you that tool real quick. Let's see what it works away. Let's work its way around here. Okay. So what's going to happen here in a corner radius mill, the point is going to come up to your control geometry. So the bottom edge, so we got a 1/4 of an inch flat area. So this point right here at the base of the tangent is what's going to touch your control geometry. And that's why we had those offset curves. And I'm going to show you that in a minute. Let's go ahead and run this. We'll go ahead and close that. We'll turn that off and we'll simulate this. And we can do pause and then to end. Okay, so we did cut levels all the way down, and you see that we're getting the start of this fillet that we want at the bottom, and it's flat right on the bottom of the flat area right here. So let's go ahead and we're going to do a parallel finishing. And as I mentioned before in that graphic, you want to give the parallel finishing room to get down here. If you select this curve right here, or if you just select all of your part, it's not going to reach it down there. It's going to stop up here. So we're going to go ahead and select this curve right here. It gives it a little bit of breathing room. This distance with the red and the red is the radius of the tool, and it's going to leave it a little bit more room to get all the way down. So we'll do that. We'll use our ball mill. For our cut parameters, this is a finishing operation, so we're going to leave it stock at 0. We're going to use a 15% step over. Now, obviously, in finishing, you're going to use a tighter step over, but we're just using a 15% so that we can get through it relatively quickly. So for Z containment, we're not going to contain it. We're going to use linear entry motions and exit motions, and we're going to use some arc fitting. And let's go ahead and generate that. Okay, so we got a parallel finishing. The blue lines are arc motions. So we got arc motions going all the way over to the top, and you'll see that the tool came all the way down and had a little bit of extra room. You could move this in some and regenerate it to see how it works, you know, in all the areas around it. If you don't want that little flat area extension, we're going to leave it there for now. So we're going to go ahead and clone this, and we're going to change. All we're going to change is the cut angle to 90 degrees. Now, one thing to note, in fitting arcs, you can only fit arcs to your 3 principal planes. So your toolpath has to follow in the X direction, in the Y direction, or obviously in the Z direction if you're doing a horizontal finishing. So you can't use a cut angle of 45 degrees. You won't get any arc motions. So we're going to change that to 90, and that changes nice finishing operation. Let's go ahead and simulate those two. Let's turn that off, and we'll do that. We do pause to the end, and then we'll do this one, and we'll do a pause to the end. So you see, we're getting a good indication of this fillet. It's not exactly done yet, so we're going to add a couple of more operations, because you see the fillet on this, you got vertical walls, which is a true, you know, quarter 1/8 inch fillet, but then you got all these contoured areas that are have a bitangent area, and I'm going to show you how to do that real quick. So let's go ahead and do first we'll do a profiling operation, and we're going to use this curve. So this is exactly 1/8 of an inch. So I mentioned in that corner radius mill, the bottom tangent flat perimeter of that mill is going to stop here, and it's going to extend upward for the radius. Let's go ahead and make sure we have the corner radius mill selected. Cut parameters, we'll determine using 3D model. We're going to do one cut at the bottom, and cut levels, it's at the bottom. We're going to leave these set to 0, which means it's going to only cut one level right at the bottom of the geometry. And we're going to use a ramp entry so we don't leave any tool marks. We'll see that 5 degrees, and we'll leave that at 0.1, and we'll not use any retract. Again, advanced cut parameters, we're going to fit arcs. We don't need any cornering. Let's go ahead and generate that. So here's our profiling operation, and let's go ahead and simulate that. So you see that it didn't really cut anything on the contoured areas because it's not all the way over and touching the part. So it didn't cut anything here, but it cleaned up the areas that you have the vertical walls. So we have 1/8 inch radius here already, 1/8 inch radius there. So how are we going to get this fillet radius in there? What we're going to do is you can use either a horizontal roughing or the horizontal finishing. It'll achieve the same result. We're going to go ahead and do a roughing. So we'll do a horizontal roughing, and this time we're going to use this larger offset here. We don't want these areas out here to get involved. With the tool, we're going to use the corner radius mill. And just one second. No, let me back up. I made her incorrect. We want to go ahead and use this one. No, that's right. This one is right. That's right. So for the tool, the clearance, cut parameters, again, this is going to be an offset cut pattern. All of these, it doesn't really matter because we're just going to have one cut level. So we're going to set this cut levels to 1, okay? And we're going to clear flats. So what's going to happen here is it's going to move that tool right up to the surface. Let's see what happens. Oh, hold on a second. I need to change my tolerance. This is a finishing pass, not a roughing pass. And again, if you have any questions, Joe will be done in just one moment. Let this calculate. Joe, we have any questions here related to 3-axis?
There were a few, but I've taken care of most of them, so
Okay. Okay.
we're good.
Okay. Looks like we're not getting a good cut area. Let's go ahead and
So
try a horizontal
make
finishing.
sure, yeah, make sure you remove stock also.
Okay. Let's remove that. We're going to select this. And we're going to stock is 0. Okay. We got 1 cut level. 0 flats. Optimize. No. Well, it's all right. Generate that. Okay, here we go. So what you see is we have a cut level in the bitangent areas. And let's do a, so you see that we have 1 cut level going around cleaning up this fillet. And then it's going to do this area here. And in this operation, that tool is bitangent to each of the contoured areas and the bottom. So we get a nice clear 1/8 inch fillet radius. And we didn't do any posting, but it's pretty much straightforward. Just right click on what you want to post and pick post, tell it where to go, and output your G code. Okay, so let's go back over to the slide presentation. Was there any questions that we need to answer now, Joe, or are we going to get back with some people, or what?
We're good. Yeah, there's a couple that we can get back on.
Okay, everyone. Apologize for having to move quickly through the demos portion, but take a look at those slides, and you can locate the tutorial for both of these parts in your online help and the resource guide. You can locate it there. Okay, if there's no further questions, we'll go ahead and
Yeah, you want to go to the next slide, Don? Just show the email addresses for people if they're not.
Sorry about that.
Yeah, just if you can go to support@mecsoft.com is where you want to go. You know, for any other questions that you might have, or if you have sales-related questions, obviously sales@mec will work. Okay. Anyway, all right. That's our contact information, and then website www.mecsoft.com, and you can get all that information there as well. So, thank you.
Okay, thanks, guys. Thanks for joining us today. Have a good day.
Bye bye.